welcome to our channel Euclid Mathematics. And I'm Swapnil sir. I'm here to help you all to help with your difficult concept. As we know that CSIR NET exam is coming, so we have started lecture series on a ring theory, group theory, and all the subject: calculus of variation, integral equation, real analysis, linear algebra. All subject I have started on my channel. I uploaded plenty of the videos for these topics. You may, if you wanted to see, you may go through this playlist and check these videos. So if you have any doubt, comment, or anything difficult you found in your textbook or in your question, you may comment me in a comment section. I will come up with the same video on my channel. So here in my today's video, I will explain to you all one of the topic like abelian group, cyclic group. Okay, so how it hold for M and R. Okay, so it is a matrix group. Okay, so how it is hold for these groups, or is there abelian or not, or cyclic or not? We need to know it because under ring theory these topics are very much important. So let's get start our today's example. I will explain to you all how the properties of abelian group and cyclic group are correlates. Here today I'm going to explain here M and R matrix with respect to n by n. Okay, order. Over ring under addition is abelian group but not cyclic. Okay, so you all need to understand what is abelian and what is the cyclic. Okay, to hold the property of abelian we have to show like a dot b which is equal to b dot a, or a star b which is equal to b star a. Okay, star is the respective operation of our group. Okay, so if this property hold, then we say that the group is abelian. Okay, but for cyclic, okay, we cannot guarantee abelian group is a cyclic. Okay, sometimes it is there, sometimes it is not there. Okay, so there is no any necessary condition that abelian it is cyclic, but always remember cyclic group is always abelian group. Okay, but what is mean by cyclic? Cyclic group means there exists in our group, there exists an element which can generate our whole group. Okay, okay, a to the power which generate our whole group. So if we found such an element in our group, then we say that the group is cyclic, or in a simple language we can say the element of a order and the group of a order. Okay, so in our group, the order of a group, if suppose order of group is a n, and if there exists an element which order is also n. Okay, so order of a group and the element of order, okay, if both are same, then we say that the group is a cyclic. Okay, so this is the way to check whether our group is cyclic or not. Okay, and there is a relation between abelian group and cyclic group too. Okay, every cyclic group is abelian, but converse need not true. Okay, and counter example I already explained in my previous lecture. You may check in my group theories playlist. Okay, already most of the examples are there. Okay, so now let's get started with one of the example like a M and R. Okay, matrix with a n by n elements, rows and column. Okay, so can we say that if mn under integer addition, ring I have taken here integer, okay, under addition is a cyclic or not? Or for mn zp, okay, z under addition multiplication, it is a ring here. Okay, and p, it is a prime element, z prime. Okay, and we know that z prime is always abelian as well as cyclic. Okay, so let's show that mn z under addition is a abelian or a cyclic. Okay, so if I consider n which is equal to 1, like a m1 of a z which is isomorphic to z, okay, which contain only the integer. Okay, so m1 of a z which is equal to only z, that means 1 by 1 matrix. 1 by 1 matrix means which contain only one element, like a, one row and one column. Okay, like this one. Okay, so if n is equal to 1, so then we can apply any property. If we add a to another element here, first a and b, consider any next one which is again 1 by 1. Okay, so if we multiply them, if we add them, if you go through the inverse, all these properties are easily hold. Okay, then we say that m1 of z which is z under addition is a cyclic. Okay, z under addition is a cyclic, then we can easily prove that m1 of z is a cyclic. Okay, which is a cyclic. m1 of z means a matrix with respect to 1 by 1 entries, and all entries which coming from integer group. Okay, so m1 of z is always cyclic. But what about for when it goes to the two elements, like two rows, two columns, like m2 of z? Okay, now let's prove this property it holds or not with one counter example. So if we take n greater equal to, that means m2 by 2 of z, that means it's a 2 by 2 matrix, then m2 of z is cyclic or not? Okay, so from if we take 2 by 2, that means surely this property hold for 3 by 3, this property hold for 4 by 4, and so on. Okay, so I consider here one counter example. Okay, it's under multiplication, it is here m2 of r under multiplication is a group or not? Okay, is cyclic group or not? Okay, so let's here I consider one counter example, m2 of R is equal to aij is a 2 by 2 matrix, and aij which is from R, and m2 R is not abelian. Okay, so if not abelian means not cyclic. Now let's see with a counter example, is it true or not? Okay, so here I consider one counter example. A is a 1 0 1 1, B is a 1 1 0 1. Okay, if A star B which is equal to B star A hold, then we say that the group is abelian. Okay, if A star B is equal to B star A hold, then group is abelian. Star B, you may take any operation. Okay, so I consider here 1 0 1 1 1 1 0 1. So this counter example play a very important role to solve our examples. Okay, so we just have to find out any one of the counter example, and we need to prove that our example is our question is wrong. Okay, so our property is wrong. So that way I consider here A and B. Now show that A star B, you may go through the multiplication or any other operation. Okay, A star B is, we get here 1 1. Okay, so multiply matrix into this one, this into this plus this into this, so it gets 1. So similarly this into this one, then we'll get this one, again this one into this one, we'll get this one, and this one into this one, this is get this one. Okay, now again multiply B into A, so B multiplied by A, we'll get it here. So as we can observe here, okay, so A star B not equal to B star A. Okay, that means M2R does not satisfy abelian property. Okay, property of a abelian group. Okay, that's why M2R, it is not abelian group. And if it is not abelian group, that means it is not cyclic group. Okay, abelian, not abelian means not cyclic, but abelian cannot guarantee about cyclic. This relation you all need to know. It is quite confusing to understand, but once you solve few examples, it's quite easy to understand. Okay, M2R not abelian group means not cyclics, but abelian cannot guarantee cyclic, and cyclic group is always abelian group. Okay, this property need to know. That means we can easily show that here M2R is not a cyclic group. Okay, so only this one, the example, counter example I wanted to explain here in order to understand the correlation between abelian group and cyclic group. Okay, I hope so you all have understood my today's lecture. It's quite easy and solely depend on the correlation between abelian and cyclic group. Okay, so thank you everyone. Thank you for my today's lecture.